Can you see my screen now? Can you see my screen?
It's still loading, Professor. We wait a couple of seconds, maybe.
Not yet.
It's okay now?
Yeah, perfect.
Okay. So first of all, I would like to thank Professor Ivo Cartini and for her the kind of invitations to give me this opportunity to talking about the my work, and also because I thought in both Ivy and I and actually representative to the both two countries, the neutron society. So I thought my talk have to be closely linked with the neutron scattering, but I realized this advanced materials conference have people different background. So that's why you see in my topic, I have using the different colors. Definitely, my talk will involve the neutron scattering technique, but I will focus on more general like structural characterizations because it is very critical in the functional materials. Functional materials, and it's very critical determine the fact for the properties. Okay, so I would maybe cut the pointer. So yeah, okay. It's okay now?
Yep. Okay.
Yeah. Okay. So I think that most people study materials you make using the retro refinement method. So this method has been developed in 1969 by Professor Redwood, named by his surname, and currently total cited like over 13,000 times, and even only like 2021, this paper PDF papers PDF has been downloaded over 15,000 times. So you can see this method is very critical for us to study the materials and to determine the structures. However, this method and the base built and developed based on the X-ray crystallography. So that's actually method give you the way to describe the crystal structures. And generally, what I want to say using my language is like average structures. Is so why I say that? So you say because you're using the X-ray beam or penetrated like a micrometer scale. Neutron, you have a large, the deeper the penetration in the materials, but you gave the overall structure in the whole materials. So that actually you say the average structure. If you base on the Bragg laws, and the diffraction will be average. So that's why we call the average structure characterized by the X-ray diffraction, neutron diffraction, and so based on the traditional Bragg law. Okay, so that we call the traditional X-ray crystallography. So I take examples, and for example, lithium neodymium titanate. There's a perovskite structure. So in this case, you have a solid solution, and actually in one lattice site, you have two elements and occupied in the same lattice size. And this is a typical, is one of the not very good, but is the typical ionic conductors for the battery materials. And you can see here, titanium was centered in and for octahedral, and then to form the frame. But lithium neodymium are randomly allocated in the cage. But lithium, you can see lithium and neodymium in the periodical table are very, very different in terms of their size, total nucleus, and electrons, and electronegativity. So all these determine, once you locate that, you want to keep the average structure, that actually to minimize the energy when they reach the equilibrium state, actually there's a lot of things going on locally. So that's what we call the local structure. You can see this atomic image. You can see this around the length scale about this total picture, and it's about 100 nanometers. 200 nanometers. You can see the lot of different features that actually is reflect the local structure determined by the local chemical inhomogeneous that means you have a different chemical composition in each region, and also because of the structure distortions and ion displacement and octahedral tilting differently as well. So all this information actually come together to give you a real case of the structure. We have done we have investigated these materials for 5 years. I remember it's like near 10 years. We identified over 280 different types of local structures, and none of them as dominated to play the dominant role as a major fixed structure feature. So that's what it's difficult, like folks, that it's not that simple, like we get average structure from X-ray diffraction. It's a simple cubic, simple cubic phase. So that's actually indicate is, of course, is an extremely case that indicated in real structure of the solid materials is very complicated, and especially solid solution. And also you can imagine if you introduce actual ions or something into these materials, depending on where they are located. So the doping will give you completely different performance depending on where they are preferred to go. So that's indicated is chemically structured, the local structure were quite different. So we really need to combine different techniques to build a real relationship between structure and the property and the chemistry of the materials. Okay, so that's why I was thinking will be give you a good give some examples, and based on our past like 15 years research, maybe more than 15 years. I would just like to try to summarize, give you an idea how complicated they are, and we need to combine different technique to look at the structure of the materials. Okay, the first of all, and we will give talking about the chemical order disorder, and then we're talking about the structure disorder locally, and also we will try. I will give one example quickly shows how if you have a small or light elements, how difficult they are to be the structure to be determined. And also I will show you like a surface bulk difference as well in the structure is quite often in the solid materials we ignore that. Okay, and also like all these things will be will be like static average structure issues, static structure issues, and also later I will discussing about the structure dynamic. Okay, so the first of all, we will come to the chemical ordering. I'm using these two examples. One is barium manganese niobate, and this is like a perovskite structure, but we have manganese niobate are quite different. So generally, if you look at this have a layers chemical ordering, you got a 1 layer manganese and a 2 layer niobiums to give this kind of the average structure. Okay, so look like a very simple. Okay, so that's work actually done by when I was postdoc stage, and so that's actually I think is a very good example for the people who study the materials. I run the XRD, and but I found the XRD pretty much in the beginning is around 1 hour XRD, and they all like metric cube, it's a cubic phase, and but when I measure the property, so the like for example here dielectric property, I found that this every time each samples are different, so it's not really consistent. So that in order to understand why, actually I very carefully to run all the samples and so all the XRDs, but instead of using the 1 hour the time to run, each samples I run one day. Okay, it's more than 10 hours, like almost 1 day during the working time. So I working now like more than 10 hours, and I found actually some peaks are splitting, some peaks are not. Because if you run quickly, like this peak splitting, you couldn't see that. So after that, actually, I try to like look at the structures composition. I found actually all the property actually located in the both. This is like a loop, the envelope, and one is extremely case like that. One is like that. Rest will be in between. Okay, so later I found actually this related to two structure. One is fully ordered, chemical ordered in the B side, and one is completely disordered. Okay, I will show you more detail what I'm doing because it's XRD give some peak splitting, so sometimes still very hard. So that's why I look at the electron diffraction and use this strong dots are the black diffraction, same as what you say in the XRD. But we couldn't say in the XRD is this is like a weak dots. All these kind of diffusion streaking, diffusion scattering, and here. And so actually you can see these two samples are quite different. One is they don't have it's only 4 dots. That's an order structure. The reason because this here it's one third satellite diffraction, and that's associated with the chemical ordering of the manganese and to the niobium 1 to 2. And but here, and you got a cross here and this order, and you look at the atomic image, you can find locally they are quite different. You got a lot of local domain, then like a contract are different. So what they are, and we do the structure refinement, we find actually if we assuming this fully ordered, you can see this B is the parameters, and you can see they are quite deep. The manganese are very unhappy. It's quite a big the thermal parameters. So that's tell you something not exactly right in your structure refinement. So what happened here, actually, we assuming the chemical ordering one layer magnesium, one layer niobium, one layer B. Actually, you have a atom stacking force, and your niobium should be magnesium, but your niobium here, and you got another layer niobium. So in that case, you can say that you got a one layer mixture magnesium niobium, one layer niobium. So you got a 1-to-1 ordering. So in that case, look at here. So this is 110,001. This is 111. You got a half 111. Okay, because of this chemical 1-to-1 chemical ordering. Okay, and then you so in real case, this is two extremely, you got a 1-to-2 and a 1-to-1 ordering, but in the middle, because you don't know the correlation length, is the stacking force can happen in the materials with different correlation length. So that's why you got this diffusion scattering here. So that they all combined together will give you like an image like the diffusion scattering as a cross section. So if we consider this stacking force of the atoms, and you will find actually the second layer is this model, and you can see the thermal parameter become much better, consistent with the other elements. Okay, so that's what happened when we do this structure refinement. We introduce the compositional atomic modeling functions, and you can see the fitting parameters getting much better. Okay, so that's tell you the chemical ordering is not really in every ideally in the average case. Okay, so locally they will be different. Okay, and all they are located if energy profile is they favor the positions, it's not big difference. So in that case, they can jump to other. So that's why you got a local chemical difference, ordering or disordering. Okay, another example is the paracels. So we call the general paracels has a A2B207, and so what happened is generally as you have a big cations occupied in the octahedral center, and you got oxygen, one type of oxygen corner link form the octahedral structure, and another one is tetrahedral network. So this tetra is actually metal in the center. The oxygen, another oxygen in a different position and in the center, and then you got A cations and will be corner connected with all these tetrahedral. So these two we call the anti-stabilized the structure, okay? And these two network, they will penetrate each other to form the whole structure, okay? So we do a lot of investigation on the different type of the particle materials, and here actually we find is two type of the materials has in terms of the property and in terms of the structure, okay? So I was using like, for example, BZN, like here as an example, you see the bismuth in A cations is only two, it's 3 out of the 4 in the A side is is a bismuth, and we call the bismuth less. And then another one, bismuth pretty much fully occupied. So in that case, we call the bismuth 2, these kind of things. So then we take the BIN and the BZN as example. I will show you how this property different, how this structure different, okay? So if we look at the BZN, BIN, you see these both are relaxed ferroelectric materials, and but this relaxation happen for BZN around 100, 200 Kelvin. But here, though this relaxation happen at high temperature range. And if we're using the same model to fix this relaxation, we find actually, and in the BZN, the freezing frequency is about THz. So that's related to the some ions movement to contribute to the relaxation. Okay, but this one is 10 to the power 20 Hertz. It's far faster than general ionic lattice vibrations and free electron vibrations. So it doesn't make any physical sense. So that tells us definitely these two types of the materials has a different origin for this relaxed dielectric polarization. What they are. Okay, so we look at, generally, if it's relaxed, it must be associated with the local small dipoles, domains, the polar domains. So that's why we investigate the local structure, because it must be local structure different. So we look at these two families, we find that this family has this kind of features, and another has a different features in local structure. So when we look at this octahedral structure to see what happened. So if you look at the average, the B oxygen chemical bonding length is about 2.05, and the niobium, either niobium or zinc in this case, and has a 1.98, 2.911. It's very close to the average structure. So they both, that means they are pretty much happy with this where they are. Okay, and but if you look at the tetrahedral network, they give you quite different capability, the stories. So first of all, because it's based on composition, we have to have each octahedral, each tetrahedral have to have 3 bismuth and 1 zinc. Rather, the other will be difficult to make because A side you need A side cation, you need 2 the oxidation states closer to 2. Okay, and then you will find that we need a chemical ordering in this case. Okay, so the bismuth zinc in the A side is not a mixture like randomly. Okay, and secondly, you look at the bonding distance. The oxygen A cations bonding in this structure should be 2.29, and bismuth zinc, you see, this far away in comparison previous one, it's far away from this structure. That means that the bismuth zinc stay there will generate some local strain. Okay, so that's make so in that case, in order to make them happy, they have to locally moving around and to release the strains to minimize the energy to stable structure. So in that case, they will generate the local structure. So what happened is, what you look at, if you have a zinc here, we know they bismuth zinc have to be 3 to 1. So in that case, that will be 3 bismuth, that 3 bismuth. So you only have one way to locate the zinc. But you look at the next zinc, so you will find that you have a different direction to allocate the zinc. So you see, go this way, zinc here, and this one, zinc here, right? It cannot be here. So in that case, we look at this 2 set possibility. So if this one, because oxygen is unbounded, so this oxygen will move into here, oxygen will move into this zinc, but this one, the bismuth will be struggling. Where should it go? Because when we go there, when they go there, if bismuth will be struggle. But if you put the zinc, and then zinc, both oxygen and the moving to the zinc because it is unbounded, and then bismuth will moving towards that, following that. So in that case, they will shorten the zinc bismuth bonding, extend this bismuth bonding. So in that case, this tetrahedral will be distorted and give you some size effects. Okay. So based on this model, that's a possible model. So we do the structure refinement. We will find here, like a model 1 is a chemical ordering, and model 2, model 3 is like based on the picture I described. So you will see here, like the last one is a new step by step. You will see this like thermal parameters changing quite significantly. Okay, so what is here is a local short range chemical ordering in these compounds and give you a local structure. So we're using the multicolor simulation, try to fit in the electron diffraction we observe. This is experimental electron diffraction pattern. You say, and then if we're using the fourth energy term is related to chemical composition, bismuth and zinc 3 to 1, you will say it's nothing to do to really look at. But if we go further to arrange the zinc in a specific way, and you say it's improve a little bit, but and then you have to, as I mentioned, the bismuth you need to shorten the zinc bismuth bonding and extend the bismuth bonding in the tetrahedral, and you say you got pretty much the main feature are very close to this electron diffraction pattern. Okay, so that means our model are correct. And if you do for other different electron diffraction collect on different zone axes, you will see they are pretty much similar. You can the model fit very nicely. Okay, so that tell you actually the local structure is like that, but how is the average? If you look at this one, if we pack them all together, you can see this average, the position always in the middles, but in real atoms, each of them are differently. Okay, so that's actually is a very nice picture tell you the local structure, each for individual atoms, and they are location is not same as your average structure you got from XRD. Okay, so that's actually, on the other hand, the bismuth Indian Laureate one, so the another family of the paracels actually is because you got a bismuth rich or fully bismuth occupied. So this tetrahedral like a rigid unit model. So it's doesn't change the bonding of the tetrahedral. And then they six come together to form the circle and you like because it's bismuth is underbounded. This oxygen, which is on the octahedral parts, actually also underbounded. So you'll see here, you have a 180 degrees, this bonding angle. So in that case, this bismuth moving towards this oxygen, and the other to moving another way. So your six tetrahedral actually form like a camera shot. In, out. So make the overall the charge balance locally and make all this chemically happy. So yeah, if we look at this different direction, you can see here you got a H octahedral tilting, tetrahedral tilt. Sorry, you got a H octahedral tilting along this direction. So that actually give you a net dipoles to make a contribution to relaxation of the dielectric property we saw here. But this one, I didn't go further. What happened, this one has nothing to do with your local structure, the relaxation. It's because of the oxygen vacancy. I didn't talking about that because today we are talking about focus on the structure. Okay, so that's actually explain that. With that one, actually we're using different model, like glass models, and to fix that, we found actually frequency is much reasonable. Okay, I don't go to the detail about that. Okay, so that is another examples on the chemical order, disorder. So That's show you the chemically you can generate the local order disordering and then give you a local structure which is different in comparison with the average and make a contribution in the property difference as well. Okay, so and the second one I will try to focus on a local structure disordering. So I was using the typical lead-free piezoelectric materials, which is with one key functional materials as well. Okay, so we know the lead, zinc, titanate are very well-known material, piezoelectric materials using for the as sensors, transducer, actuators for different kind of application. Actually, application everywhere. For example, your ultrasonic imaging using in a hospital. So this also using this kind of materials. Because lead is toxic, is now over past 20 years, and a lot of work have tried to find a lead-free one. Okay, and so for example, this system, material system is one example. But no matter lead contain or lead containing or lead-free and the systems, we find actually lead, the piezoelectric property will present the optimal performance in this boundary, which we call the morphotropic phase boundary, and actually is between rhombohydroferroelectric and tetrahydroferroelectric. So it has been the question why this materials has the optimal performance here for many years. And one easy way people think, whoa, that will be like the two-phase region. You got two-phase, but you physically put two-phase together, never have a good performance. Okay, so this definitely is not two-phase. And secondly, and the people using the XRD or neutron diffraction try to interpret that, and they found that actually it's a monoclinic phase. Okay, in average, but you can say if we can systematically change the chemical composition, you wouldn't expect the lower symmetry phase and will be stay in the two stable high symmetry phase. That doesn't make sense. Okay, so in that case, so that's actually draw our attention many years ago or try to investigate what's going on here. And we come back to the structure analysis people has done before. We find actually, if we do the structure refinement, you say this is the highest peak. These curves reflect the difference between your fitting curve, the patterns, and your experiment pattern. Generally, you expect the variation difference will be this one will be biggest one, largest one. But you can say here it's not. This one is the big largest one. So that means this peak is always underestimated in the structure refinement. And also interesting, people index this one as 0 to 4. But if based on the average structure, this materials, this symmetry shouldn't, this peak you shouldn't see. Okay, let's tell us something must be going wrong or haven't revealed and uncovered, and is in these materials. Okay, so that's why we will look at this. We found actually based on the average structure, it's people, not only one, two people that do the work, structure refinement. We found that actually bismuth is very unhappy. So bismuth oxidation should be 3+, but locally only 2.4. Okay, so it's definitely underbounded. Sodium slightly underbounded. That tells you locally that the crystal chemistry point of view is unhappy. So that this is something locally must be going on. Okay, so in that case, we investigate the electron diffraction. We find that this is a strong peak is related because it is rhombohedral. This material is rhombohedral structure. You got the octahedral tilting along the 1-1-1 direction, and one rotate this way, one rotate the opposite way. So that gave you a satellite diffraction here, half 1-1-1. But you can see that the one peak I thought it shouldn't be there is one half 1-1-0 of the parent structure. So it's actually, it should be here, but they do have here those. And also most interestingly, these two satellite diffraction are linked together. So that means you have an intergroup structure occur locally, happen here. So the half 111, because I mentioned it's a rotation, it's based on the average structure, but half 110 should be there, but it's there. This actually reflect the octahedral tilting around the 001 interaction. That means the implant, the rotation tilt, octahedral tilt. So that's tell you locally you have a local structure disordering. That came either you can say like this one. This different color is a different rotation. You have an octahedral rotation stacking force, or and they give you a twinning structure in very fine scales. So that's actually only few nanometer. So that's make your structure refinement more very difficult. Okay. So and then if you look at, we do that because it's ferroelectric. We want to see what happened on the electrical field, and we do the in situ neutron diffraction in the different electrical field. That electrical field like a 3 kV on the samples enough to switch them to the ferrite to get all the polarization aligned. Okay, so we found actually from this one. It's very, if you don't consider the local structure, you got a very large, the good of fitting the parameters like 16. That's absolutely unacceptable in this case. However, because the locally you can have this kind of structure, and you can have this structure. This locally look at individual like a PM and A. A space group, but it can combine them together because they have both cases, and then we can take them as the average cubic PM by 3 structure. So we're using assuming this local structure, the contribution can be described by this cubic structure. So in that case, we can determine how this local structure change in volume when you apply electric field. Okay. So, and here the PO is the preferred orientation, because we have to consider that, because when you apply electrical field, the the polarization domain will be switched. So that gives you a feature in the structure is our preferred orientation. So you have to consider that. But you see, we got a model 1, model 2, model 3, and 4, and eventually you can see these GOF parameters get 5.9 is well accepted. Okay, so surprisingly, we will find actually the 70% of the octahedral tilting has been changed without changing average structure. So that's a very, very big things. And once, so that tell you actually when you apply electrical field, you have introduce the largest string change and the polarization change. Actually, your average structure doesn't change. So it can that came from octahedral tilt. And then we look at the systems, because you're using the chemical way, add more barium titanate to try to switch the phase in the boundary region. We found actually, you can see here, that's the end member BNT, and you have add more BT in the morphotropic phase boundary. You can see this one, this satellite diffraction, actually much stronger than half 111. Okay, so that's actually tell you octahedral tilting in this morphotropic phase boundary play the important role for the optimal to achieve optimal piezoelectric performance. So that's actually is the first time we observed that. And what happened? But you may ask, what happened in this phase transition range? So what happened is in this range, when you increase the barium titanate and gradually you have much strong octahedral, you have more octahedral tilting in different way, and also there are correlation length change as well. And until a certain chemical composition, which is beyond this range, the average structure completely damaged. So let's go to the tetrahedral. And you can see that it's quite different now. Okay, so that's actually tell you in the morphotropic in the boundary regions, no average structure change. only local structure change to the certain extent and suddenly change it to another structure. Okay, so that is a local structure disorder, and that how they will affect the property a lot. Okay, so that's a chemical ordering and structure ordering, and in general case. And now I will put talking about another part, like if you meet lighter elements, small elements, what may happen, and on the surface bulk, what may happen. Okay. So I just using very quickly using this example to show you what happened. So this is a lithium doped barium titanate. Everybody just like lithium is small, and everybody just doping everything in the materials. And so like, for example, doping in the A side and interstitial dopings, the property change significantly. Like for example, take a large amount of 7% is a big property change. But remember, you doping anything in your materials, they will change the property, right? Because it's you got something additional, right? But where they are and how they affect the property, that's very critical for like from materials chemistry point of view. So that's why we found actually all these materials, none of them has a pure phase. Okay, property change, but that's mainly came from the multi-phase. And then we do have one in the, if we put the lithium in the nominal composition in the B side, the titanium side, to replace the titanium, we find that one, if we go to 5-7%, they do from XRD or the neutrons, they all get the pure phase. Okay, so that's why we focus on that to study how this happen. And but within lithium, like 7%, you wouldn't see in the XRD, right? But that's why we do the neutron. But we didn't see that as well. So that's make we are very puzzled why lithium cannot say such a 7% large amount of the lithium cannot be seen by neutron. Okay, and then we try to using NMR, lithium NMR, solid NMR, to try to collect the lithium. The information we find actually large, about 75% of the lithium in the amorphous phase. Okay, in the here give a big peak here, very broad big here, A peak, and only very small the lithium amount of lithium in the lattice side in the crystal structure give you a different BC D peak depending on where they are located. And also interestingly, we try to using the DFT and theoretical simulation to figure out what happened is here. Also, we do the ESR identified we have titanium-3 as well. Okay, and actually what happened, when you doping the lithium to replace the titanium, it's not like a one lithium occupy one titanium position. Titanium will never be there. What happened is you take one titanium away, you have a 4 lithium in that octahedral range. And 2 lithium are very close to titanium side. Other 2 lithium is away, more close to the edge of the between the barium and the titanium, okay, side. So and these 2 titanium, the far away from the titanium side, these 2 lithium actually is dynamic. You couldn't detect that. And that's actually also make a contribution to this A peak rather than BCD. Okay, other 2 closer to the titanium side actually make a contribution to the B and the BCA side. Okay, and then you have a defect cluster as well, coupled with the titanium-3, give you another lithium peak. Okay, in here. So that show you it's very complicated in this case where the lithium located. I think most people will maybe never think about actually you got a 1 octahedral, you have a 4 lithium located in that region. Okay, so yeah, so that definitely will give you large, because that lithium located in this way. And then in that case, the titanium is not like a barium titanate, all the titanium move in a correlated way, give you a ferroelectric property, and you got actually titanium can move up. So you got a dipole up, dipole down, give you ferroelectric, anti-ferroelectric like behavior. Here, you observed here. Okay, so that's the lithium small one. So when we have a small one, we have to be carefully to calculate structure. And another example I want to give to you is the surface. So that's related to the anti-ferroelectric materials, which you can be using for energy storage. Now using a lot, anti-ferroelectric become very hot the last few years because you can store the energy. Okay, and also this anti-ferroelectric, when you apply electric field, you always have a phase transition from anti-ferro to ferro, and you can have a reversible or non-reversible phase transitions, and so you can use it for the reversible energy storage or the explosive energy power conversions as well. So we take this example here, typical anti-ferroelectric, they are chemical composition located in the phase boundary. Okay, which is interesting. A lot of people working on that, but nobody really understands what's the structure of these materials. Why? Because if we, XRD, as I mentioned, it is averaging in the micrometer scale, right? And neutron actually give you a bug because the neutron can penetrate it deeply in your materials. So actually, I using these two complement to each other to give me the information on the surface, how the surface structure change, how the bulk structure change. It's very interesting. We found actually in the neutron, this structure is ferroelectric with this space group. And in the XRD, they are different. You have an antiferro and a ferro. Okay, so look like very confusing about that. So what happened, what we think is something maybe already changed halfway between antiferro and ferro. So as a result, we deliberately design, we're using one big sample, we cut it into 4 pieces. And then one we treat as a fresh sample, another one we polish the surface, and the third one, after the polish, we heat treat at 600 degrees to release the stress. And then with the third sample, we polish it again. We take it out from 600 degree furnace. So that's the difference. You can find actually it's XRD, and they can see the structure change, but the neutron you don't. So that's tell you the bulk materials has a ferroelectric phase, but the surface has different. And also, you know, we want to measure the surface property and the bulk property compare to see if they are consistent with structure. Okay, we're using the piezo force microscope and to indicate that to characterize. We found a fresh sample we cannot characterize because the roughness is too high. But with surface, this rest 3 sample we characterize the polar have a polarization domain, and we say the surface polish is a 2-phase, and then after the heat treat is the 1 phase, and then you polish it 2-phase again. So that's actually when you look at the bulk property, we put an electrode on both sides of ceramics, and we found the property doesn't change. It's a very electric. So that's give you this picture consequence. So actually, all the bulk materials are ferroelectric, structure ferro, but surface, because you treat them differently and actually give you a different picture. That's why in the literature, where people very confusing where their property came from, and they never find the consistent structure and property this correction. So before this work, okay. So that's an example. So then finally, I have a few minutes. Still have a okay.
Yes, Professor, you have 2 minutes left.
Okay, so I will quickly talking about the structure dynamics. Okay, so the one example is the zeolite, which is similar as what I mentioned, the Laureate unit mole. But this one is a very clear picture without any structure. So zeolite has a tetrahedral aluminum. For take this one as an example, you have an aluminum tetrahedral phosphate hydrohedral. They link each other to give a porous structure. If you look at the different direction, you can see the 1 layer aluminum tetrahedral, 1 layer phosphate. And you can see clearly diffusion scattering there. And then I do the simulation. It's well nicely fit, this one. So what happened is because you have you can see here, this oxygen, actually you have metal, oxygen, metal, aluminum, oxygen, phosphate angle is 180 degrees. So that gives you uncertainty, instability to like have this kind of octahedral chain. So we look at inelastic neutron scattering, and we do the molecular dynamic simulation. We find actually at high temperature, because of the thermal fluctuations, the oxygen here is just randomly like circled. And when you drop a temperature, you can see a circle, and then you can see the oxygen jump 1.5 K. So, okay, it's very interesting. We are looking for the even low temperature to say if you can freezing. Maybe we want to try to millikelvin to say if this jump can be freezing. So that's a very low energy. You can excite this octahedral tube, the oxygen bonding. Okay. Another is perovskite. We know perovskite. We work in perovskite many years, but never been hot because recently, because the hybrid perovskites make solar energy transfer the electricity with very high efficiency. So that's actually draw our attention to see how the molecular perovskite will change. So we'll take this because if you have a ligand linker that octahedral together, you have more flexibility, and also you can increase the freedom. And for example, you have a conventional tilting column shift. And so we take the MORPH as an example, okay, and put different ligands in this cage, and we find actually the structure different, and then the hydrogen bonding are different, and most importantly, we see the property are different as well. So in order to understand what's going on in this property, you see this is a big relaxation on dielectric property, and there is some relaxation, but you also see some here is not a linearly increase. So this one doesn't change much. So we actually try to using the inelastic neutron and to quasi-elastic neutron scattering. The strong one is the neutron scattering, is a elastic one related to the black diffraction, but we integrate them together. But the narrow peak is a quasi-elastic, and then broad peak will take more further, and it's inelastic. So in that case, we do the simulation, we try to understand what's going on in this case. So actually, this one, like you say that we have hydrogen has a different trace if you say at a different temperature, different time. So that's you can say the blue one is more related to the nitrogen bonding the hydrogen, and the green one is the carbon one. Carbon one more CH3 are more flexible. Okay, and the same things we do for the hydrogen in DMA and hydrogen in the GUA. They are different. Overall, you will say all the signal actually originate from internal rotation of the maximum group, and they have different configurations. CH3 rotation will be different with different time, and the hydrogen bonding with the nitrogen has more limitations. Okay, so that's the things. And also we look at the A side, because of the magnesium, how magnesium working, how this octahedral connection angle happen. So we do have a look at this one as well. They are quite different. So you can see this the A side move the angle related as well. Okay, and then you look at this one is also we look at the whole frame. So this is a magnesium distance moving on different MORPH, and this is the oxygen carbon oxygen bonding here, this angle, how this change. So you can see they are very flexible, provide a lot of detail, help us to understand the property. This is inelastic high energy parts, and then give also, you do the simulation, give you more information. So in the end, this one came from the structure, phase transition with a different space group. And this one actually is also the structure phase transition from commensurate to the incommensurate structure. Okay, and this one is related to the hydrogen, the slightly change of fluctuation property is based on the contribution carbon nitrogen bonding and the hydrogen in the A side. Okay, so that's pretty much all the examples I want to show you. And so the structure characterization, which is very critical and for materials design and for the understand the properties. So, and finally, I would like to thank my colleague, Professor Revises, Professor Richard Weberis, and also these all doctors is my students, they graduate and become academic staff now. And also I have a lot of neutron work and actually supported by the instrument scientists in Aston, Australia Nuclear Science Technology Organization. So this is two postdocs, they have been done the work at that time in my group, and also thanks the funding support. Okay, and maybe I have take a few minutes to pick up question. Thank you.